Relativity is about two people agreeing about what they see when one of them is moving. When that motion is at a constant speed in a straight line, we say the observers are in an inertial reference frame.
Yes, Einstein's relativity for inertial reference frames is called his special theory of relativity.
And in it, he postulates that any person moving at a constant velocity will observe the same laws of physics that a stationary person observes.
I take it from your little performance that you're going to tell us about frames of reference that are speeding up or slowing down or changing directions.
Absolutely. Do you think that Einstein's principles still hold? Can we say the laws of physics are the same for observers in accelerated frames? Does light travel at a constant velocity in non-inertial frames of reference? Jeeves, start it up, please.
Let's put you in a closed room in deep space, millions of miles from gravitational influence of any planet. You can float about the room effortlessly. Objects at rest remain at rest. Objects in motion float along a straight line until they collide with a wall. But if rocket engines attached to the room began to accelerate you through space, you would feel something quite different. You would feel yourself pushed by the accelerating floor. Objects at rest would seem to fall as the floor accelerated up to meet them. If the acceleration were large enough, you would be able to stand and walk about just as you would if you were back on Earth, subject to the attraction of gravity. In fact, Einstein argued, there's no way to tell the difference between being stationary under the influence of gravity or being accelerated through space. And since all observers must agree on the basic laws of physics, the laws of physics that describe gravity must be, in some sense, equivalent to those that describe acceleration through space. According to the general theory of relativity, the presence of matter in the universe alters the geometry of space. One way to visualize what happens is to imagine a bowling ball being placed on a trampoline. The bowling ball distorts the surface, causing the other objects in the vicinity to move towards it. Something like this is responsible for the force of gravitational attraction. Even though we have been able to calculate the strength of gravity since the time of Isaac Newton, we never really had a clear picture of how gravity works. An apple falls to earth, we would say, because some invisible force of attraction between the apple and the earth pulls them towards one another. But what causes this gravitational force? How does this attraction happen? Nobody really knew. So Einstein did away with the idea of an invisible force altogether. There's no mysterious force pulling the apple towards the earth. Rather, the presence of Earth in space causes a curvature of the surrounding space-time. And the apple simply follows the most natural path available to it as it moves through this curved space. In this case, a path that causes it to move towards the Earth. If Einstein was right, and massive objects really do curve space itself, then gravity should affect the motion of everything through that space, even light. Imagine the light from a distant star traveling past the sun. According to Isaac Newton, gravity is an attraction between all objects with mass, and since light has no mass, the star's light would be unaffected by the sun's gravity. But in Einstein's picture, a massive object like the sun bends space itself. So starlight moving through the curved space should be bent by gravity. Who was right? It would be hard to tell. The deflection of light predicted by Einstein's equation was tiny. And besides, you can't see the light from stars that lie behind the sun because the sun is too bright. You need to be able to see the stars in the daytime. Luckily, just 4 years after Einstein's 1915 publication of the general theory of relativity, there was a solar eclipse due to occur across the Atlantic Ocean from northern Brazil to the coast of Africa. Astronomical expeditions were sent to both of these locations, equipped with telescopes and cameras to photograph the stars as they become visible behind the blotted out sun. If Einstein was right, the apparent positions of these stars would be shifted away from their true positions photographed months earlier, when the sun was in another part of the sky.
The result? The astronomers announced that Einstein's predictions were confirmed. Relativity was quickly accepted by scientists, and it wasn't long before Albert Einstein became a household name.